Is gravity real? Well, we're all firmly planted here on the ground in this wonderful venue, not bouncing around the room. And what about light? Well, we can look each other in the eyes, so I'm pretty sure light is real. Sound? Shoot, I forgot to do the mic check. Check 1, 2. You guys hear me? Good. What about the latest scientific buzzword of the day, quantum? Quantum is notoriously counterintuitive and just plain weird. Something feels different about it. And some of the most famous scientists in the world, Nobel Prize-winning scientists, have said as much. For example, Richard Feynman said, if you think you understand quantum mechanics, you don't understand quantum mechanics. And Roger Penrose said, it makes absolutely no sense. And even Albert Einstein claimed that if it's true, it spells the end of physics as a science. Curious. And these guys actually won their Nobel Prizes for their advancements in quantum. So what is it anyway? Well, the basic idea behind quantum is that everything is a thing, and in physics we call things particles. So every particle is a thing, but it also behaves like a wave. It moves like a wave. In other words, wave-particle duality. And the way that physicists interpret this wave is a probability function. It's telling you the likelihood of finding the thing at a particular place at a particular time. And I love this electron diffraction experiment. For the nerds in the audience, Young's famous double-slit experiment. What they've done is they've poked 2 holes in a metal plate, and they're shooting a beam of electrons at it. Now, if you were doing this with golf balls, you'd expect the golf balls to just pile up in 2 piles behind each hole, right? That's not what happens. The electrons actually pass through both holes at the same time. And they bend around the holes and add up on the other side in a constructive way where the wave gets bigger, and sometimes they cancel out and the wave gets smaller. And so you see this periodic pattern forming as the electrons build up on the other side of those metal plates. And this is proof that the electron is behaving like a wave. Now, guitar players, musicians understand waves. As they slide their finger down the guitar string, they make the wavelength shorter, and so the pitch goes up. They also understand that at each end of the string, there's no vibration. The vibration is maximized somewhere in the middle. Sailors and surfers understand waves because they've seen them bend around jetties. And as they crash on the beach, sometimes those waves add up and make a bigger wave, and sometimes they sort of cancel out. And I think perhaps quantum dots provide one of the best examples, and maybe one of the most beautiful examples, of quantum and its impacts in our everyday lives. If you don't know what quantum dots are, these are vanishingly small particles of semiconductor, nearly impossibly small, on the order of tens of atoms or so in diameter. And just to give you a sense of how small that really is, if you took a golf ball and compared it to the size of the Earth, that same ratio would apply to the size of a quantum dot to a golf ball. So let's let that sink in for a second. A golf ball on the Earth is like a quantum dot sitting on a golf ball. So impossibly small. And when you make particles, these little bits of material that small, you confine the electron. And remember, it's a wave, so it has to fit in that little box. And if you make that box a little bit bigger, going back to the golf ball analogy, if you made it the size of a tennis ball, it would have a little bit lower energy, a little bit larger wavelength, and so the color of that might be a little bit more red. And if you made it a bit smaller, like the size of a marble, it would have higher energies. You squeeze the electron, and the color would be a little bit more blue. So even though these particles, these quantum dots, are the same composition of matter, we can tune their color by just changing the size of the particles, which is a new vector in materials optimization. They have this other really very valuable property that they're fluorescent. So not only can you tune the color of light that they absorb, but you also can tune the color of light that they emit, which makes them a platform for all sorts of different applications. So when I was in school, I studied electrical engineering and physics before I got a PhD in material science, and I found myself at Los Alamos National Laboratory in the chemistry division. And I had an opportunity to start a company to spin this technology out about 10 years ago. That's when I formed Ubiquity, which is short for ubiquitous quantum dots. with the notion that quantum dots are actually going to become widely used, so much so that they're everywhere. And so when I started the company, I was thinking about raising some money and started talking to investors, and that's when I met Catherine. Catherine ended up becoming one of my first investors and a board member. I really love that lady. And she came to my office one day, very excited, super excited. What if we could use quantum dots to make glowing nail polish? I thought this was the most brilliant idea I'd ever heard. I was inspired. So I ran to the grocery store, picked up some clear coat nail polishes, and threw some quantum dots in there, let it stir overnight. Came back the next day, and lo and behold, I had a couple vials of glowing quantum dot nail polish of different colors. And I think I might be the first human being on the planet that put quantum dot nail polish on their fingernail. So I got that going for me, which is nice. But that was just the beginning. Once you had a clear coat that you could use to make things glow, you could coat just about anything. So we had the idea, maybe you could make a bike reflector glow in bright red and make it more visible at night for a safety value. So we made some prototypes, and actually it worked pretty well. Going back to the golf ball analogy, I hit my ball right down the middle of the fairway. I don't know about you guys, but I have some friends that have this problem. Sometimes they'll lose their ball. But we figured if you had a glowing golf ball, you might be able to find it more easily. So we applied a little bit on some golf balls, and it looked pretty cool. Fast forward to today, and we're making all sorts of different things glow, every color in the rainbow. One of the coolest applications is actually in agriculture. It turns out the reason why plants are green is because they don't absorb green light very effectively. They're reflecting that back to your eyes. But they absorb red light, orange light most effectively, and then blue next. And so we are embedding this technology in the facade of a greenhouse, in the roof and the sides, and just glowing down on the plants with some orange light actually makes them grow faster, up to 30% faster. This same concept actually works in solar panels too. If we can shift the color of sunlight, you can make a solar cell actually be a little bit more efficient as well. So this technology, just by shifting the color of light, is actually making food and energy production more efficient. Pretty cool, right? So this year we're celebrating the 100th anniversary of quantum mechanics. And for the nerds in the audience, that's the 100th anniversary of when Schrodinger wrote his famous wave equation. Some of the earlier concepts, there were some concepts that were ideated earlier than that. Einstein actually won his Nobel Prize a little bit earlier than that. But Scientific American was trying to celebrate this, so they did a survey asking more than 1,000 physicists, is quantum mechanics like reality, or is it just a mathematical tool that helps us understand reality? And only about 40% of them said that it partially represented reality, and 17% said it was a complete description of reality, which I find just shocking. Because I guarantee you that 100% of those scientists would agree that quantum mechanics has never been proven wrong. Every experiment we've conducted has validated it, and its predictive power is unparalleled. Cell phones and smartphones and smart technologies like transistors, solar cells, all rely on quantum to be developed and function. But it goes much further than that. Quantum is required for us to understand how chemical bonding works, what light and color actually is, and indeed why plants can use light to grow, and even global warming. Some scientists have even speculated that consciousness in our brain comes about because of a quantum mechanical effect, the entanglement of states between different neurons in our brains. So our ability to be curious may actually be a quantum effect too. Pretty cool. Quantum exists because of the curiosity of scientists like Albert Einstein. And they struggled with it. Albert Einstein famously said that he couldn't accept that God could play dice, this whole probability function thing. Before quantum, in physics, everything was deterministic. If you knew the laws of physics, you knew the initial positions, you could literally predict the future. But quantum says, no, that's not how it works. We only have a probability of a future A, and we have a probability of future B. But Einstein said something a lot more impactful, in my opinion, than that. He said that creativity is more important than knowledge. And nanotechnology gives us the ability to build up materials atom by atom, and indeed quantum dot by quantum dot. And at the nanoscale, there's infinite possibilities of how you could combine materials in different sizes and shapes. And to quote Richard Feynman again, There's plenty of room at the bottom. So is quantum real? Does it even matter? Like gravity, optics, and sound, it just works. And if you need an example, come on up to Los Alamos and check out some of our glowing quantum dot materials. Thank you.